Welcome to our deep dive. Today, we're tackling a shape you probably see all the time, maybe without thinking much about it. The triangle.
That's right. We've looked at a bunch of source material covering, well, everything from the basics, definitions, types, to the rules about their angles and sides.
And our mission here is to pull out those key insights, the things that really make you feel well-informed about triangles. Ready to jump in?
Let's do it.
Okay, so starting right at the beginning. According to the sources, what is a triangle, fundamentally?
It's quite simple, really. It's defined as a plane figure, so flat, and it's closed, bounded by three straight line segments.
Segments called sides, yeah.
Exactly. Those are the sides.
And the points where the sides meet, vertices, the sources say?
Correct. Vertex is the singular, vertices for plural. And you'll often see that little symbol, delta, used for it.
Right. The standard shorthand. So 3 sides, 3 vertices, closed figure. Simple enough. But then the sources immediately start classifying them. It seems there's more to it than just triangle.
Oh, definitely. The sources break it down 2 main ways.
Yeah.
You can classify them based on their sides, or you can classify them based on their angles.
Okay, let's take sides first. What have we got? There's equilateral.
Yes, equilateral. Think equal. All 3 sides have the exact same length.
Okay, equal sides.
In a really interesting consequence the sources highlight. Because the sides are equal, the angles inside also have to be equal. They're all 60 degrees. It's perfectly symmetrical.
60, 60, 60. Got it. What's the next type based on sides? Isosceles.
Isosceles, yeah. That's when just 2 sides are equal in length.
Only 2.
And another property pops out here. The sources show the angles opposite. Those 2 equal sides are also equal to each other.
Okay, so 2 equal sides means 2 equal angles opposite them. That makes sense. And the last one for sides is scaling.
Scaling. That's the one where no sides are equal. All 3 sides have different lengths.
And I guess that means no equal angles either.
You got it? No equal sides, no equal angles. It's the most irregular one by side length.
All right, so sides, equilateral, all equal, isosceles, 2 equal, scaling, none equal. Now, what about classifying by angles?
This is probably just as familiar. Maybe the most common one people think of is the right-angled triangle.
Yes, the one with the perfect corner.
Exactly. One angle is precisely 90 degrees, that little square symbol in the corner.
Okay. Then there's obtuse angled.
Right. An obtuse angle is one bigger than 90 degrees, but less than 180. So an obtuse angled triangle just needs one angle like that.
Just one wide angle makes it obtuse. And the last one?
Acute angled. That's where all 3 angles are acute, meaning every single angle is less than 90 degrees. They're all sharp angles.
Okay, so we can classify by sides or by angles. That gives us a quick way to describe them. Now, the sources move into some really core rules, like fundamental truths about triangles. Theorems, they call them.
They do. And they make a point of distinguishing theorems which need proof from axioms, which are just accepted as true. And yeah, the sources often provide proofs for these big triangle theorems.
That's what I found interesting. They show why these rules work. Like maybe the most famous one about the sum of the angles inside any triangle.
Ah, yes. That's absolutely fundamental.
Yeah.
The sources state clearly the 3 interior angles of any triangle always add up to 180 degrees.
Always 180. Never more, never less.
Exactly. And the proofs shown in the sources often involve drawing a parallel line, which neatly shows how those 3 angles fit together perfectly on a straight line. It's quite elegant.
That 180 rule feels like a cornerstone. What's another major angle theorem the sources cover?
There's one about the exterior angle. If you, extend one side of the triangle straight out.
Okay, draw one side longer.
Yeah. The angle formed outside the exterior angle is equal to the sum of the 2 interior angles that are opposite to it, the ones it doesn't touch.
Wait, hang on. So the angle on the outside equals the 2 far ones on the inside added together.
Precisely. So if you have triangle ABC and you extend side BC out to a point D, that exterior angle ACD is equal to angle A plus angle B lot. The sources derive this from the 180 rule, actually.
Huh. That's less obvious, but super useful, I bet. It shows how these rules connect.
They really do. And another key connection the sources draw is between the size of the angles and the length of the sides opposite them.
Oh, right. How does that relationship work?
It's pretty direct.
Yeah.
The bigger the angle, the longer the side that's opposite it.
And the other way around, too. Longer side means bigger angle opposite.
Exactly. They scale together. The greatest side is always opposite the greatest angle, and the smallest side opposite the smallest angle.
Okay, that makes intuitive sense. And this leads to another big rule, doesn't it? The triangle inequality theorem.
Yes, absolutely crucial. The sources state it very clearly. If you take any two sides of a triangle and add their lengths together, that sum must be greater than the length of the third side.
Right, because if it wasn't, they wouldn't be long enough to meet and form the triangle. They'd just lie flat or not reach.
Exactly. You couldn't connect them. AB plus BC has to be greater than AC, for example.
And the sources mention a sort of flip side to that, too.
Yeah, a related consequence. The difference in length between any two sides is always less than the length of the third side. It's another part of that same geometric constraint.
And this whole side-angle relationship explains something like why the hypotenuse is the longest side in a right-angled triangle?
Spot on. The right angle is 90 degrees, which has to be the largest angle in a right-angle triangle since all three add up to 180. So the side opposite that 90-degree angle, the hypotenuse, must be the longest side. It follows directly from that principle in the sources.
Wow, okay. So we've gone from the basic definition, three sides, closed figure, through the classifications, equilateral, isosceles, scalene, and then, right, obtuse, acute.
Then into those core theorems. The angle is always summing to 180, that exterior angle rule, and this really important link between side lengths and angle sizes, including the triangle inequality.
We've covered quite a bit of ground drawing straight from the source material.
We really have distilled the key properties and relationships.
So here's a thought to leave you with. Think about how these simple, fundamental ideas about triangles rules, discovered maybe thousands of years ago, how do they become the essential starting point, the real building blocks for almost everything complex we design and build? In engineering, architecture, even computer graphics and physics. How does this simple shape underpin so much?